All right, so um, there is a new Bacon quiz available on substitution reactions. We talked about the Bacon quizzes a bit last week. They're an opportunity to replace your lowest quiz score, so you can work on that. And then exam number 2 is coming up. It's going through chapter 8, which we're starting today. And so exam number 2 is going to be Wednesday through Friday of next week, which means that on Tuesday next week at 7, we're going to have one of those online Zoom question and answer sessions. That means that we'll be filming a review, an outline of all the topics tomorrow, and we should have that up, the link up on Learning Suite by the afternoon tomorrow. So anytime between tomorrow afternoon and Tuesday, you should take a look at that review, that outline of the topics, and come prepared to the Zoom session on Tuesday to ask questions. So today we will complete chapter 7, finish our discussion of the SN2 and the SN1 mechanisms. And then we'll start chapter 8, where we'll be learning about eliminations, another type of reaction of alkyl halides. Since the products of elimination reactions are alkenes, we'll spend some time talking about the structure and stability of alkenes, and then we'll start talking about one of the two mechanisms of elimination, the E2 mechanism. But where we left off was looking at the different factors in substitution reactions and deciding whether they would favor SN1 or SN2. We talked about the type of alkyl halide, the nature of the nucleophile, the nature of the leaving group. The last one we have to consider is the solvent. We have our two types of solvents, our polar protic solvents and our polar aprotic solvents. We, of course, need to be able to identify them and classify our solvents. Which reaction would be preferred with a polar protic solvent? SN2 or SN1? Okay, I see SN2, some people answering. Why? Some people saying SN1, okay. So polar protic solvents actually are preferred for SN1 reactions. We'll say they're best for SN1. Why is that? Okay, go ahead. Okay, solvates is the term that we would use. Yep. Okay. So, of course, the key step in the SN1 reaction is the formation of the carbocation. Okay, that's our rate determining step. And our polar protic solvent is able to solvate the carbocation using ion dipole forces. Could a polar aprotic solvent solvate a carbocation? Yes, it could. So if a polar protic solvent is better, there must be something else. Yes. Okay. So a polar protic solvent is also capable of solvating the leaving group, which is an anion. So a polar protic solvent can solvate both products of the rate determining step, whereas a polar aprotic solvent would only be able to solvate one of the products of the rate determining step. Since the rate determining step of the SN1 reaction is endothermic, we know that more stable products are going to be formed faster. So if we can lower the energy of the carbocation in the leaving group through solvation, we're going to lower the energy of the transition state because there's going to be solvation at the transition state as well. Solvation of the partial carbocation and the partial leaving group. So an SN1 reaction is still going to be slow, but it's going to be less slow if we're using polar protic solvents versus polar aprotic solvents. And in many cases, the polar product solvent is also the nucleophile. Most of our weak nucleophiles are polar product solvents, water, methanol, ethanol, and so forth. Okay? So we're usually going to see polar product solvents used in SN1 reactions. Okay? So what about polar aprotic solvents? What are they best for? Yes. Yes, polar aprotic solvents will be best for SN2. Why? Yes, Claire. Exactly. So in the SN2 reaction, our nucleophile is participating. Our nucleophile is almost always negatively charged, and therefore it can be solvated by a polar protic solvent, but not solvated by the polar aprotic solvent. We don't want solvation of our nucleophile because that slows down the reaction. So no solvation of the nucleophile in the polar aprotic solvent means that SN2 reactions would be faster in polar aprotic solvents than in polar protic solvents. Any questions? Okay, so we have a table here that is summarizing the information we've discussed at the end of Wednesday's class and at the beginning of today's class. And of course, the alkyl halide is the first thing you want to look at when deciding if a reaction will be SN1 or SN2. The one thing I want to caution you about on this table, I mentioned this on Wednesday, I wouldn't really say that weak nucleophiles favor SN1. What I would say is that weak nucleophiles prevent SN2, so all you're left with is SN1. This would give you the impression that you won't see SN1 reactions with strong nucleophiles. You most certainly can. In fact, the first one we showed you in class used acetate as a nucleophile, which is a strong nucleophile. If you have a tertiary alkyl halide and a strong nucleophile, you will have SN1. Right? You can't have SN2 because it's tertiary. You can only have SN1. So please don't think that you can only have SN1 with weak nucleophiles. You can have them with weak or strong. What they're trying to say is that if you have a weak nucleophile, it has to be SN1. That's what they were trying to say. They just didn't word it quite correctly. Any questions about the table? Okay, so a couple of other things to talk about before we move on to chapter 8. We talked a little bit about substitution reactions in biochemistry. We referred to S-adenosylmethionine, nature's version of iodomethane with that very, very large leaving group with the positive charge on sulfur. There's another type of biological leaving group, and that is these phosphate derivatives. The diphosphate is the most common one, but you can see any of these used as leaving groups in biochemistry. And you see that we have multiple negative charges in these cases, but these are good leaving groups. They are not basic. Okay? Why are these not strongly basic, even though they have multiple negative charges? What can we do with the negative charges in these phosphates? Yes. Yeah, they're resonance stabilized, so those negative charges are shared by all the oxygens. That negative charge is quite delocalized. And so that's what makes diphosphate and these other species effective leaving groups that you see used frequently in biochemical substitution reactions. They can be used in either SN2 or SN1 reactions. And the example shown here on this slide is an SN1 reaction. And this comes back to something we talked about on Wednesday. Ordinarily, you wouldn't think that you could generate a primary carbocation, but why does this primary carbocation form in this case? The answer is right here. It's resonance stabilized, exactly. So we said that if you can form a resonance stabilized primary carbocation, it's not really a primary carbocation because the positive charge is shared by two different carbons. And so that's what's happening here. We generate this resonance stabilized cation. Water attacks as our weak nucleophile, and we get the final product. Another principle that's not explicitly mentioned here is that if you have a resonance stabilized carbocation and you have that positive charge on two different carbons, either of those carbons could get attacked by the nucleophile. So in principle, you could have two different products from the substitution of this carbocation. The fact that only one is shown comes from the fact that this reaction occurs in the active site of an enzyme, and the enzyme brings the carbocation and the water together in such a way that it only reacts at the terminal carbon as opposed to the internal carbon. But if you didn't have an enzyme, you could get two different products from that reaction. Okay. All right, and then back at the beginning of chapter 7, we mentioned that vinyl halides and aryl halides, where you have your halide attached to an sp2 carbon, do not undergo SN2 or SN1 reactions. Now that we've learned more about those mechanisms, we can explain why these reactions do not occur. So over here, and this figure here is showing the vinyl halides, but the same explanation is operative with the aryl halides as well. So the sp2 carbon and the planar geometry here causes a couple of problems. First is that as the nucleophile approaches from the backside of the leaving group, which is required for SN2, it would be approaching very close to these pi electrons. And so you would have a repulsion that would prevent that from happening. And then the second problem is that since our sp2 carbon is planar, the nucleophile would have to approach in the same plane as these two groups that are pointing towards it. So you would have a lot of steric hindrance as well. So electrostatic repulsion combined with steric hindrance is going to prevent an SN2 reaction from occurring on a vinyl halide or an aryl halide. Question? So in a tetrahedral carbon, those groups are not in the same plane as the nucleophile when it comes in. But in a trigonal planar carbon, for this to come in at the back side of that group, it has to be in the same plane of all other groups that are attached to that sp2 carbon. And that just doesn't work. So you might think, well, we can have SN1 instead. It's going to be slow, but it can still happen. The problem with SN1 is if you lose a halide from a vinyl halide, you have what's known as a vinyl carbocation, and the positively charged carbon is sp hybridized because it only has two groups attached. And it's a very unstable situation to have a positive charge on an sp carbon. The easiest way to think about it is to notice that there are only two groups attached to that sp hybridized vinyl carbocation. And so you have less groups available to donate electrons to that positively charged carbon, so it's going to be high in energy. So it's just not going to work, too high in energy. And again, the same thing would apply to an aryl halide as well. Any questions? Yes, please. If you could form it, it would. But if it's high in energy, usually the barrier to form it is even higher. And so that's the problem we face, is we can't get over the barrier to form that kind of a species. Okay. All right. The last part of the chapter talks about organic synthesis. We're going to largely defer that discussion to later on in the class when we've learned more reactions. But this table is important because it shows us many of the strong nucleophiles that we've learned about in chapter 7. And it shows us the types of products that we can obtain from SN2 reactions using these strong nucleophiles and alkyl halides. So what makes the SN2 reaction so useful is that we can take a single type of starting material, an alkyl halide, and react it with a nucleophile of our choice, and we can generate a whole bunch of different types of products. So we'll see SN2 reactions frequently throughout the class as we get into organic synthesis, which we'll do in the next section of the class. Okay. Any other questions on chapter 7? Yes? Yes, they are. Exactly. They certainly are. And so, and we'll, like I said, we'll address that when we get into the next unit of the class where we learn more reactions and we'll start talking about multi-step synthesis. Okay, good point. All right, so let's go into chapter 8 now. Chapter 8, also about alkyl halides, but talking about the elimination reaction. Like there were, in the same way there were two substitution mechanisms, we have two elimination mechanisms, an E1 and an E2. And so alkyl halides can actually react by four different mechanisms, SN1, SN2, E1, or E2. So a major focus of this chapter is being able to look at the type of alkyl halide, the type of nucleophile or base, and predicting which of those four mechanisms will occur. Before we do that, let's talk generally about eliminations. We learned some things about eliminations in chapter 6. We learned that eliminations are reactions where two groups are lost in the starting material, and in their place we form a pi bond. So we're going to have a base. Most of the time that base will be negatively charged. It doesn't have to be, but most of the time it will be. That base is going to deprotonate what we would call a beta hydrogen. So there's some Greek letter nomenclature that we can use with alkyl halides. We can say that the carbon bearing the alkyl halide is the alpha carbon, and the carbon adjacent to it is the beta carbon. So we remove a beta hydrogen atom. We form a pi bond between the alpha and beta carbons, and then we lose the leaving group. And so that gives us an alkene product. It gives us the conjugate acid of our base, and then we also have the leaving group. Okay? And the base usually has a cation that goes along with it that would form a salt with our leaving group, but we typically don't draw the spectator cations. So how many bonds and what types of bonds are broken in this reaction? Okay, we have two sigma bonds breaking. What bonds are being formed? A pi and a sigma, okay? So if we look at it that way, we would say that it's going to be endothermic because pi bonds are weaker than sigma bonds. And they can be endothermic, but the other thing to consider is that the leaving group is much, much less basic than the base. And so we're converting a strong base into a weak base, and that provides a driving force that counteracts the fact that the weaker bonds are being formed and stronger bonds are being broken. Okay? I've drawn it as a concerted process. It does not have to be. Sometimes it's concerted, other times it's stepwise, as we'll see later on. So the specific type of elimination that we will discuss in this chapter is referred to as dehydrohalogenation. That is a mouthful. It takes a lot of space to write it across the board. Dehydrohalogenation is just referring to the two groups that are being lost in the reaction, a hydrogen and a halogen. So that's where the name comes from. Okay? So this table right here shows us, whoops, I didn't mean to press that button. I don't want to do that. This table here shows us some common bases that are used. And you see they're all strong bases. Okay? We can actually use weak bases. We'll learn about that later next week. But the vast majority of the time in dehydrohalogenation, we will be using strong bases. We recognize hydroxide bases as strong bases from general chemistry. And then these other ones, these alkoxide bases, are the conjugate bases of alcohols. Okay, those are strong bases comparable to hydroxide in their basicity. So the one at the bottom here, potassium tert-butoxide, is a special base. So if we were to react a primary alkyl halide with any of these other bases, we would have an SN2 reaction because primary alkyl halides are the fastest in SN2 reactions. And these strong bases are also all strong nucleophiles. But we mentioned this in chapter 7, tert-butoxide is so sterically hindered that it is a weak nucleophile. So if we want to perform an elimination instead of a substitution, then tert-butoxide is the one to use because the substitutions don't occur since it is bulky. Okay, so tert-butoxide would form an alkene, would perform a dehydrohalogenation of a primary alkyl halide. So this particular primary alkyl halide I've drawn for you just has a single elimination product, a single alkene that could form. So what if we had the constitutional isomer 2 bromopropane as opposed to one, or butane as opposed to 1 bromobutane? How many different alkene products could we get from a dehydrohalogenation of 2 bromobutane? Okay, I see a lot of people raising 2 fingers. Who would like to raise their hand and describe for the class what those 2 products would look like? Okay, go ahead. Okay. Like this. The terminal carbon is what I would call it. Okay. So you're saying these are the 2 products. And that's because we have 2 different sets of beta hydrogens. These 2 sets of beta hydrogens are not equivalent to each other. And so if we remove beta 1, we would get the one over here. If we remove beta 2, we get the one over here. But there's actually 3 products that can form. And that comes from a property of alkenes, which is that you cannot rotate about the carbon-carbon bond of an alkene. So we have this product which has the double bond in the middle, and it has the methyl groups on opposite sides of the double bond. But we could also have a product where we have the double bond in the middle and the 2 methyl groups on the same side of the double bond. These are isomers of each other. They're stereoisomers. What kind of stereoisomers are they? Okay, they're cis and trans isomers, so you've read the book. That's good. More generally, cis and trans isomers, what type of stereoisomers would they be? They're diastereomers, exactly, because they're not mirror images. They're stereoisomers. They're not constitutional isomers. The atoms are connected together in the same way, and they have a different orientation in space. But since they're not mirror images, they are diastereomers of each other. Question? So if the double bond is on which end? Yeah, so because we only have 2 sets of beta hydrogens, that tells us that we have 2 different constitutional isomers that could form. So this double bond, this alkene and this alkene are constitutional isomers. But then because of the properties of this alkene that we'll talk about in a little more detail, we end up having the ability to have a diastereomer of that alkene. So first we see 2 constitutional isomers, and then we see one of those constitutional isomers has a diastereomer that could form. Okay, yes, Claire. Beta hydrogen is a hydrogen on the carbon adjacent to the leaving group. Whenever we're performing an elimination, we are deprotonating adjacent to the leaving group. And so we have to have beta hydrogens. That's one feature of elimination reactions. We have to have at least one beta hydrogen in order to perform an elimination. So let's talk a little bit about the structure of alkenes. I brought a model of ethylene here. So what's the hybridization of the carbons in an alkene? sp2. What's our geometry? Trigonal planar. What are our bond angles? 120 degrees. Okay. So we have a classification system for alkenes that we need to go over. When we have alkenes other than ethylene that have substituents attached, then we classify alkenes according to how many substituents and where those substituents are located. So if we only have one substituent on our alkene, we would say it is a monosubstituted alkene. And then two substituents on the same carbon, they could be the same substituent or they could be different. We will call that a 1,1 disubstituted alkene. And then we could have our two substituents on different carbons. That's going to be a 1,2 disubstituted alkene. And of course, we could have cis and trans isomers of this. And then we have trisubstituted. And then, of course, we could have tetrasubstituted alkenes. Okay? So I mentioned to you that we cannot rotate about the carbon-carbon bond of an alkene. Question? Are you talking about this one? Oh, this one, 1, 2. Because we're just referring to the two carbons of the alkene. So this group is on one carbon of the alkene. This group is on the other carbon of the alkene. So we would just say 1, 2 for that reason. Of course, if those are carbons, you would have at least 4 carbons in the chain. But we're just looking at the two carbons of the alkene. So we see here in this figure, we cannot rotate about the carbon-carbon bond of an alkene. And so these two species are different molecules, whereas in an alkane, they would just be different conformations because you could just rotate from one to the other. And so we use the cis and trans nomenclature. Some of you mentioned it. You read the chapter already. And it's the same nomenclature we used with cycloalkanes. When we have two groups on the same, coming off the same side of the ring, either the top or the bottom of a ring, we call those cis. And if we have our two groups, our two alkyl groups coming off the same side of our alkene, we refer to that as cis. And then trans is when those two groups are on opposite sides of our alkene. Okay, so it's nomenclature that we're familiar with. And then there's another figure. This one is not from our textbook, but you can take a look at it on Learning Suite. And this shows what would have to happen if you were going to convert a cis isomer to a trans isomer or vice versa. As you rotated about the carbon-carbon double bond, at the highest energy point, you would have those p orbitals completely perpendicular to each other. So you would have zero overlap between your p orbitals. You would have no pi bond at that point. You'd have to completely break the pi bond to rotate and convert cis into trans or trans into cis. And it requires too much energy to break the pi bond, so that doesn't happen. All right, somebody in the last hour asked if you could do that on the sun. Maybe you could, but I've never been there. And since this class is only the organic chemistry on Earth, then we're going to say that you cannot just heat up an alkene and interconvert it. Now, pi bonds can break, but they break in chemical reactions. They don't just break if you heat up an alkene. And so cis and trans isomers, they will not interconvert, and that's what makes them isomers. That's what makes them different compounds. On my model, I have my rubber bands here to represent a double bond. If I were to try to rotate I would break the rubber bands, which would be symbolic of breaking the bond. I don't want to hit myself in the face, so I'm not going to do that. But you see that because we do not rotate about the double bond, the cis and trans isomers are different compounds. Okay? So, which is more stable, cis or trans? Someone raise their hand. Yes. Okay, trans. Why? Okay, yep. We have steric hindrance in cis. The two alkyl groups are too close together, and they're opposite in trans. So trans will be more stable than cis. We'll go into a little more depth on that in a moment. But first, we have to define the circumstances under which you will get cis and trans isomers, because not all alkenes will have cis and trans isomers. Some will and some won't. In order for an alkene to have cis and trans isomers, the two groups on each of the alkene carbons have to be different from each other. So X has to be non-equivalent to X prime, and Y has to be non-equivalent to Y prime. Okay. Now X can be the same as Y. If we look at our example, our cis and trans 2-butene, each of those carbons has a methyl group. So you could say X equals Y. Each of those carbons has a hydrogen. You could say X prime equals Y prime. But if you look at each individual carbon, they have two different groups. They each have a methyl group and a hydrogen. And that's what enables them to have cis and trans isomers. So if we look at a monosubstituted alkene, could we have cis and trans isomers with a monosubstituted alkene? We could not, okay? Because we're always going to have two hydrogens on one of the carbons of a monosubstituted alkene. What about a 1,1 disubstituted alkene? Could we have cis and trans isomers? Nope. We're always going to have two hydrogens, same reason. 1,2 disubstituted, yeah, we're always going to have cis and trans isomers in this case. And then or this one is tetrasubstituted. I forgot to write tetrasubstituted up here. But with tri or tetrasubstituted alkenes, it depends. It depends on the groups. Sometimes you would have cis and trans isomers, other times you would not. Question? Yes. Yes, alkenes are the products, and so that's why we're taking a little time here to understand the types of products that you would get from these reactions. Okay. All right, so one other thing to mention is that in rings, we can have alkenes in rings. If those rings have less than 8 members, they can only accommodate a cis double bond. So if we draw cyclohexene, you see it's got a cis double bond. Try and draw it with a trans double bond. It won't work. Here's our trans double bond. This is 4 carbons. Could we put 2 carbons to span the distance between these 4? It would be impossible. Right? So the smallest ring that can accommodate a double bond is 8 members. So 8 and larger, you can have cis and trans isomers. 7 and smaller, no. Questions? All right, so we said that the trans alkene is lower in energy than the cis alkene. And with 2-butene, that difference in energy is 0.7 kcals per mole. Okay. But what may be surprising is if we compare the relative energies of cis 2-butene and 1-butene, which is our monosubstituted alkene. Cis 2-butene is lower in energy than 1-butene, than our monosubstituted alkene. And that difference in energy is even bigger than the difference in energy between the cis and trans isomers. It's 1.7 kcals per mole. Okay? So the difference here is explained by steric hindrance. It's costing us 0.7 kcals per mole to have these methyl groups on the same side of the alkene. But why is our di-substituted alkene more stable, even though it has steric hindrance, than our monosubstituted alkene? Yes. Okay, it definitely has to do with the location of the double bond and the number of substituents. And I'll give you a hint at coming up with an explanation, which is that whenever you have a result in organic chemistry that goes against what you would expect based on sterics, usually you have to think about electronics in order to explain it. Okay? Okay, yes, you're on the right track here. So let's talk about sp2 carbons of alkenes. An sp2 carbon has higher percent S character than an sp3 carbon. And we know that means that those hybrid orbitals are closer to the nucleus. Electrons in those orbitals and bonds involving those orbitals will be attracted to that carbon more strongly. So we could actually say that an sp2 carbon is more electronegative than an sp3 carbon. And so what that means is that if you have alkyl groups attached to an sp2 carbon, they can donate electrons to that sp2 carbon, similar to what we saw with carbocations. Okay? So the more alkyl groups you have attached to your alkene, the more electron donation you have from those alkyl groups to the more electronegative sp2 carbons of the alkene. Okay? So the more substituents you have on your double bond, the more stable or lower in energy it will be. And so that is an electronic effect. So the difference in energy between the cis and trans isomers can be referred to as a steric effect. And then the difference in energy between cis and our monosubstituted alkene is referred to as an electronic effect. Okay? It's explained in terms of either electron donation in this case, or other types of electronic effects would be due to electron withdrawing. Okay? So we have to consider steric effects when we're comparing alkenes sometimes to see if one is more stable than the other. Other times we would need to consider electronic effects. Questions? Okay, so let's talk about one of our mechanisms of elimination. As I mentioned, there are two. And the first one we'll talk about is called the E2 mechanism. So we're going to take a strong base like hydroxide. We're going to react it with an alkyl halide. Here I've drawn for you a tertiary alkyl halide. And in an E2 mechanism, our base is going to deprotonate one of our beta hydrogens. The carbon-hydrogen bond will break, generating a pi bond between that beta carbon and the adjacent alpha carbon. But if we do that, we have to break a bond at the alpha carbon, so then we expel our leaving group. We generate an alkene. In this particular example, we're generating a 1,1 disubstituted alkene, so there's no cis and trans isomers. We're generating the conjugate acid of our base, water in this case, and then we're generating bromide. As I mentioned, there would be a spectator cation going along with our hydroxide, but we just don't show that in the reaction. Okay, so experimentally, it was determined that this reaction is second order. Okay, the rate depends on both the concentration of the hydroxide or the base more generally, and the concentration of the alkyl halide. That was determined experimentally. And so because we have this particular rate equation, the simplest mechanism that explains it is a concerted mechanism where both reactants are participating and all of the bond breaking and bond making is occurring simultaneously. Okay, and we refer to this as the E2 mechanism. Okay, the E is standing for elimination, and the 2 is standing for bimolecular. Any questions? Let's look at an energy diagram for the E2 mechanism. They've exaggerated the difference in energy between reactants and products. Usually it's close, fairly close to each other. As I mentioned, depending on differences in basicity between the base and the leaving group, it can vary. But anyway, here we have our reactants. Here we have our products. And then you see the transition state is kind of complicated because we have more bonds that are being broken and formed than we've seen before in a single step. And so at this transition state, we have an oxygen-hydrogen bond that is forming. We have a carbon-hydrogen bond that is breaking, a carbon-carbon pi bond that is forming, and then a carbon-halogen sigma bond that is breaking. And so you see kind of this big smear of orbitals all kind of smeared together because we have a lot of overlapping orbitals, some that are overlapping less as we proceed through the transition state due to the bonds breaking, some that are overlapping more due to the bonds that are being formed. But if we were going to draw this transition state on the board, it would look something like this. And I'm just going to use B for a generic base. There's going to be a partial bond between the base and our hydrogen. Partial bond between the hydrogen and a carbon. We have a sigma bond between our carbons, but we also have a partial pi bond that is forming. And then we have a partial bond between the carbon and the bromine. And then, of course, we have other groups coming off of these carbons. I'm just going to draw those like this. These are not just methyl groups. They could be a combination of hydrogens and alkyl groups. And then we note that the base in the starting material has a negative charge, and then the conjugate acid is neutral. So we're going to have a partial negative charge on our base, and that charge is decreasing as we pass through the transition state. And then we have a partial negative charge on our leaving group, and that partial charge is increasing as we're passing through the transition state. So we'll go ahead and put brackets and our double dagger around our transition state that we've drawn. We notice we have 4 partial bonds, 2 being formed and 2 being broken. Any questions? Yes? That's a good question. SN1 reactions are slow because they depend on the formation of a carbocation. And so the formation of a carbocation is going to be slower than this E2 reaction. So that's why if it's a competition between E2 and SN1, the E2 is going to win because you don't have to wait for a carbocation intermediate to form. Okay, good question. If it was not tertiary and it could undergo SN2, you might have competition. That's an issue we'll address next week. But that's an important issue that we will discuss in this chapter. So let's talk about hybridization. What's the hybridization of these 2 carbons and the alkyl halide? When it's an alkyl halide, what's the hybridization? sp3. In the product, when we form the alkene, what's the hybridization? sp2. So what's the hybridization of these 2 carbons at the transition state? sp 2.5 is a good answer. It's going to be in between sp3 and sp2. So this is a reaction where the hybridization changes, and it's not an either-or proposition. It's not a flip of the switch. We can have hybridization in between sp3 and sp2, and that's what we have as we traverse this energy diagram. We're going from sp3 at the start to sp2 at the finish. When we're at the transition state, we're in between. Pretty close to halfway in between, I would say, in most elimination reactions. Okay? So what's the geometry going to be at the transition state? We don't have a single term that describes that, but it's going to be in between tetrahedral and trigonal planar. So I've tried to draw it that way where it's kind of flattened out. It's not actually tetrahedral, but it hasn't gone completely flat to trigonal planar. It's somewhere in between. And if you look very closely at the way they've drawn the transition state in this figure, you can also see that. You can see that in the alkyl halide, it's our typical tetrahedral geometry. In our alkene, it's definitely trigonal planar, but here they're flattening it out. It's getting closer to trigonal planar, but it's not there. It's somewhere in between tetrahedral and trigonal planar. So that's another important thing to note about the transition state of an E2 reaction. We have an intermediate hybridization state and an intermediate geometry at those carbons. Any questions? All right, we'll stop there and have a good weekend, and we'll continue with our discussion of the E2 reaction on Monday.